In Chapter 7, we're going to learn about creating confidence intervals, and first we're going to talk about the population proportion. So a point estimate is a single value used to estimate a population parameter. The population sample proportion, is the best point estimate of the population proportion. An unbiased estimator that we learned about in the prior chapter, we're going to use p-hat as the point estimate of p because it is unbiased and the most consistent of the estimators that could be used. Let's work an example with Facebook. A Gallup poll was taken in which 1,487 adults were surveyed and 43% said they have a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. Because a sample proportion is the best point estimate of the population proportion, we conclude the best point estimate using this sample would be 0.43. The confidence interval or interval estimate is a range of values rather than a point estimate that's used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated with a capital C and capital I. The confidence level, which is 1 minus alpha, such as 0.95 or 95%, is the confidence that the interval actually contains the population parameter, assuming the estimation process is repeated a number of times. This is also called the degree of confidence or the confidence coefficient. And some commonly used confidence levels are shown in this table: 90%, 95%, 99%. The most common one is 95%. We must be careful to interpret the confidence intervals correctly. There's a correct interpretation and many different and creative incorrect ones of the confidence interval that we just obtained for the Facebook users. And the confidence interval there goes from 0.405 to 0.455. The correct interpretation, we are 95% confident that this particular interval, which goes from 0.405 to 0.455, actually contains the true value of the population proportion. An incorrect interpretation is there's a 95% chance that the true value of p will fall between 0.405 and 0.455. The 95% doesn't have to do with a probability or a chance. It has to do with how we construct the interval. Another wrong interpretation is that 95% of sample proportions will fall within that interval. And a confidence level of 95% tells us that the process we're using in the long run, if we took repeated samples of the same size 95% of the time, the intervals calculated from those samples would contain the true population parameter. And here's an example here. We have 20 different samples. 19 of those captured the true population proportion, and one of them did not, which is where we get the 95% from. And critical value is simply the number that separates the sample statistics that are significant or not significant. It's basically the number of standard deviations you are away from the middle of the distribution. And for instance, if we wanted to find the critical value corresponding to the 95%, we did this in the last section actually, we come up with 1.96. And if you remember, empirical rule told us about 95% of the data were within 2 standard deviations, and actually the actual value is 1.96. And again, we could think about that. There's the confidence level. We're 95% confident that the true population parameter falls within this interval. There's a 5% chance that it doesn't. And the critical values, again here, this would be the number of standard deviations you are on either side of the population proportion. And there are the values there. And the margin of error, when the data from a simple random sample are used to estimate a population proportion, the difference between the sample proportion and the population proportion is an error. The maximum likely amount of that error is called the margin of error, and we're going to designate that by a capital E. There's a probability of 1 minus alpha, such as 0.95, that the difference between p hat and p is E or less. The margin of error is also called the maximum error of the estimate and can be found by multiplying the critical value and the estimated standard deviation of the population, of the sample proportions rather. And there's the formula for it. Now, we're not going to focus so much on the formula. We're going to derive our margin of error from the actual confidence interval. So to construct a confidence interval, here's some definitions that we need. P is the population proportion, p hat is a sample proportion, n is the number of observations that we have, E is the margin of error, and then Z alpha over 2 is our critical value. We need some requirements here. We have to have a simple random sample. We have to meet the conditions for a binomial distribution, a fixed number of trials. Trials are independent. two categories of outcomes, success and failure, and the probabilities remain constant for each trial. And we have to expect to get at least 5 successes and 5 failures. And here's how the confidence interval is built. It's going to be p hat minus the margin of error is the lower bound, and p hat plus the margin of error is the upper bound. Sometimes it's written in that format, sometimes it's written in a more shorthand format where we say p hat plus or minus the margin of error. Round off rules. You're going to round off to 3 significant digits. So procedure, we are going to use technology, and I will tell you in your homework, the problems are going to ask you to give the margin of error before you give the confidence interval, but we're going to do the confidence interval first, and from the confidence interval, we'll derive the margin of error. And to find the point estimate for P, if they give you the confidence interval, take the upper bound of the confidence interval plus the lower bound over 2. To find the margin of error from the confidence interval, take the upper bound minus the lower bound and divide by 2. So the formulas look a little similar, but notice the difference here. You're adding and then averaging between the upper and lower bound. Here you're taking the range basically of the interval and dividing by 2. So we noted in that Gallup poll that 43% of respondents had Facebook pages, and we had a sample size, number of observations, 1487, and the p-hat was 0.43. Find the confidence interval, the point estimate, the confidence interval estimate, the margin of error, and then there's a question here about whether we can safely conclude that fewer than 50% of adults have Facebook pages. Requirement check. The polling methods were done by Gallup, so that should be a random sample. The conditions for a binomial are satisfied. There's a fixed number of trials. The trials are independent. 2 categories, either the person has a Facebook page or doesn't. Probability remains constant. And with 43%, we have 639 people with a Facebook page and 848 do not. So both of those are greater than 5. Now in StatCrunch, what you're going to do is you're going to select Stat, Proportion Stats, one sample with summary. You're going to enter in the number of successes. And how did I get the number of successes? I took 0.43 and multiplied by 1487. The number of observations. And then down here on the Perform, I'm going to do a confidence interval, and I'm going to make sure it's set to the correct confidence level, in this case 0.95. And there's my output. There's my sample proportion, or point estimate. There's the lower limit of my confidence interval, and there's the upper limit of my confidence interval. So my interval goes from 40.5 to 45.5. The margin of error, remember the formula, upper bound minus lower bound divided by 2, it's 0.025. Write this in the form of p-hat plus or minus e. So we know that p-hat was 0.43, and e, the margin of error, was 0.025, so we can write it this way. And another way we can express it is like this: p-hat minus e less than p-hat plus e. Again, I know p-hat and I know e, and I can write it in this form. So based on the confidence interval obtained in Part A, it does appear that fewer than 50% of adults have a Facebook page, because the interval goes from 40.5% to 45.5%, which is well below the 50% limit. So here's one statement that summarizes the results. 43% of adults have Facebook pages. That percentage is based on this Gallup poll of randomly selected adults. Give the sample size. In theory, in 95% of such polls, the percentage that should differ by no more than 2.5 percentage points, the margin of error, in either direction from the percentage that would be found by interviewing all of the adults. When analyzing results from polls, consider the following. The sample should be a simple random sample, not a convenience sample. You should be given the confidence interval, confidence level, the sample size, and the quality depends on the sampling method and the size of the sample, but the size of the population is usually not a factor. Never think that poll results are unreliable if the sample size is a small percentage. It's simply going to make your confidence interval wider. And let's do another example, finding a sample proportion and margin of error. So we've got an article on high-dose nicotine patch therapy, and it included 71 subjects. 70% were abstinent from smoking at 8 weeks. Use a statement to find the point estimate, the margin of error, and the confidence interval. So for the point estimate, we're going to use the 0.7 from the study, 70%. We want to find the 95% confidence interval using StatCrunch, and from the confidence interval, we'll find the margin of error. So we know p-hat is 0.7. We need the number of successes, so we're going to multiply 0.7 by 71, and we get 49.7, and we're going to go ahead and round that up to 50, and we've got 71 observations. So in StatCrunch, we're going to use proportion stat, one sample with summary, enter the successes, the observations, and the confidence interval, and select confidence interval, make sure it says 0.95. Here's my output. So my margin of error, here's my confidence interval, goes from 0.598 up to 0.810. And then I want to find the margin of error, so I'm going to take the upper bound minus the lower bound over 2. Okay, now let's move in now to do population mean. So that was all in proportions. Now we're going to do means. Now, if you remember the central limit theorem, what we learned about in chapter 6, when a random sample is drawn from a population with mean mu and a standard deviation sigma, the sampling distribution has a mean of mu and a standard deviation of sigma divided by the square root of n. An approximate normal distribution as long as we had a large sample size, which was greater than 30. The larger the distribution, the closer it is to normal. Now let's say we wanted to look at some Angus cows, and they're normally distributed with a mean of 1,309 pounds and a standard deviation of 157. What does the central limit theorem say about the mean weight of a random sample of 100 cows? So it says the sample means will average 1,309, the population mean, and the standard deviation of the sample mean will be sigma over the square root of n, which comes out to be 15.7 pounds. And again, there's the sampling distribution. It's approximately normal. And we know that based on the empirical rule, we can read that off the figure here. The challenge of the central limit theorem is that it tells us that the standard deviation of the sample mean is sigma over the square root of n. And we'd like to use that for confidence intervals and also for hypothesis testing. Unfortunately, we almost never know sigma. And so what we're going to do is use S, the sample standard deviation. And we can use that as a standard error of x bar, the sample mean, as S over the square root of n. But it doesn't quite have a normal distribution. We're going to have a little bit of error if we assume that it was normal distribution. And a man named William Gossett came up with new models, one for each n, each sample size that works better. And he was actually a brewer. He worked at Guinness. And he did experiments with beer, and he had very small samples. And he came up with distributions that were bell-shaped, but the details were a little bit different depending on the sample size. And he called these the student's t distribution. And if you notice, the normal distribution is the dotted line. The student t distribution, the peak here is a little bit lower, and then we say the tails are a little bit flatter. It's kind of a spushed out distribution. As the sample size increases, it becomes closer and closer to the normal distribution. For every sample size n, there's a different student t distribution, and we work with another parameter here called degrees of freedom, which is going to be n minus 1. And this is similar to the n minus 1 in the formula for the sample standard deviation. It's the number of independent quantities left after we've estimated the parameters. So when we construct confidence intervals here for a population mean, we're going to be working with these parameters here. The population mean is mu, the number of sample values is n, x bar is the sample mean. We're going to use E again for margin of error, and S is going to be our sample standard deviation. Two requirements, simple random sample, and then either or both of these conditions are met. The population is normally distributed or the sample size is greater than 30. And again, similar formula we had for the population parameter. We're going to use the t distribution here, that's the critical value, and then we're going to use S over the square root of n. And again, we're going to use technology, so we're not going to worry too much about finding critical values. In the original data, the round-off rules, when using an original set of data, round the confidence limits to one more decimal place than the original set of data. And again, here, instead of using a z-score now, we're going to be using a t-score. And when we get into the next chapter, you'll see the use of that when we do some hypothesis testing. So we're going to use a student t distribution. And remember, each sample size is going to have a slightly different distribution based on the degrees of freedom. And again, there's another picture of how the normal distribution is the green line here. And then the student t distributions are going to be a little bit lower peak here and a little bit fatter tails. Still bell-shaped and symmetric. Okay, so procedure. Verify the requirements are met, simple random sample, and it's population normally distributed, or your sample size is greater than 30. You're going to use sigma's unknown, so we're going to use n minus 1 degrees of freedom and technology to determine the desired confidence interval. The margin of error is going to be done exactly the same as we did for the population parameter. And again, we're going to round confidence intervals to one more decimal place than was in the original data. So let's do an example. We have 15 birth weights of girls for which n equals 15 and the mean was 30.9 and the standard deviation was 2.9. And we want to construct a 95% confidence interval estimate of the mean weight of all the girls. So it is a simple random sample. Because the sample size is 15, the population is, and the requirement didn't tell us that it was normally distributed. So we're going to have to investigate normality. Remember, we learned about that in the last section in chapter 6. And here is a normal quantile plot. And this does appear to be normally distributed, no deviations from normality. So in StatCrunch, you're going to select stats, t-stats instead of proportion stats. One sample, this time we have a summary. So we're going to enter the sample mean, the sample standard deviation, the sample size, and then click on perform confidence interval and make sure you have the appropriate confidence level there. And here's my output. Here's my lower limit, there's my upper limit. So the confidence interval goes from 29.3 up to 32.5. Well, it should be 0.5, sorry, it says 0.4 there. It should be 0.5. And margin of error is going to be 32. This should be 32.5. I apologize. It might come out a little tiny bit different. Let me just check real quick. It should be 1.6 instead of 1.55. There's your margin of error. Now here's another example, and I wanted to pull this one up. I'm not going to pull StatCrunch up, but I'm going to show you what to do. You're going to click here. You've got data provided this time, so you're going to click there to open it up in StatCrunch. And the difference in the commands this time is going to be stat, t-stats, one sample with the data. You're going to select the column, and then you're just going to have to select, they want a 98% confidence level here. So you're going to just click on the confidence level. This is actually easier. And then here's your same output. And the confidence level here goes from 3.49 up to 4.28. Same calculations for margin of error, upper bound minus lower bound over 2. And there's your margin of error.